So good morning all of you, and a very happy Independence Day today. And today we are going to start with this new topic of refraction and reflection seismology. And before we go into that, as per the routine, we should go for the recap of the previous lecture. So in the previous lecture, we did talk about site characterization and couple of site characterization techniques, and the shear wave velocity is the best indicator of the stiffness, and our aim is to find out the shear wave velocity for the top 30 meters in the ground in order to design the building structures safely in an area. And this is the NEHRP program. They have proposed some guidelines for classification of the site class. This has been updated, and we need to look for it over the net. And these are some of the surveys that we should discuss about. So refraction surveys, surface wave surveys, MASW, SASW, downhole surveys and crosshole surveys, and these are some of the published literature. So we also had an idea about what is ambient noise. So ambient noise is generally considered as the background noise that is widespread noise present everywhere, which may be excited because of the oceanic excitations, atmospheric activities, human activities, and it mostly consists of surface waves. Low frequencies are called microsize, that may be generated due to the cause of the oceanic waves. And thereafter we discussed about HVSR technique, which is also known as Nakamura technique, and we had a tutorial yesterday about this technique where we learnt about how to compute the HYV curve using geopsy. And for HYV curve computation, you needed a 3-component seismogram for a period of at least 30 or 20 minutes. Thereafter, you divide it into a several number of segment windows, and on each window you perform fast Fourier transform in order to get the spectrum of the horizontal and the vertical components. And even before that, you also would like to use the anti-triggering algorithm in order to remove any transient noise related to short burst or maybe related to spikes or other unwanted signal that is not stable within that feature. Now thereafter you can simply divide the horizontal component with the vertical component, and that will be the indicator of the amplification factor at that particular soil site. And this is the application of HVSR. So we learnt about how to find out the fundamental frequency, and we would like to avoid those fundamental frequencies to be matched with the resonance frequencies of the building, and it can be used to determine the depth of the bedrock and the sedimentary thickness, can be used for the seismic microzonation, site classification and other civil engineering purposes. Thereafter we saw the CISAME guidelines. It can be used to determine whether your HVSR is reliable, whether it is getting a clear peak or reliable peak in the HVSR curve. Thereafter we also had a look on the case study published by Mr. Ravindra Gupta in 2021 for the area of Nirsa, which is just 40 km away from here. We divided the area into 3 by 3 km and recorded our observations for a period of 30 minutes at each observation point, totaling up to around 81 observations. So these are the HVSR curves that we got, and then after we used modeling techniques in order to convert them into the shear wave velocity profile up to 60 meter depths. And now these are the few figures that may give you a kind of idea how the interpolation of various shear wave profile along a array may look like. So here you can see the bedrocks are coming, and some of the some of the features that is high velocity features associated with the hard rock is also present, and also for the low velocity layers. So thereafter we learnt about the spectral analysis of surface wave. In short, it is known as SASW, and it was first given by the people at University of Texas at Austin. And in this technique you do use the dispersive characteristics of the Rayleigh wave that travels through the various layers of the earth, and then using that dispersive characteristic you would like to find out the dispersion curve after using a couple of receivers with the source. And for this purpose the field setup may look something like this. You can see there is a source here and there is a receiver, and the source to receiver distance, if it is x, then the between receiver it will be also the same. Thereafter you had the recording and you can change the setup and can replace this R1 to R3, and thereafter your distance will change to 2x, and thereafter you will keep on repeating it, and then you will get a nicely looking dispersion curves. Then you will integrate them together in order to get a composite dispersion curve. And then these were some of the sources that we just looked at yesterday, and this was the procedure that we just explained. And for this purpose you can use a software SASW to get your shear wave velocities from the dispersive characteristics of the Rayleigh wave. Now thereafter we learnt about the MASW technique. In MASW technique also we do use the dispersive characteristics of the Rayleigh wave. We try to measure the dispersion curves along an array of receivers. So basically you have a geode that can be 24 channel, 48 channel or 96 channel, and you will connect it to the various receivers, and thereafter you excited the source either in the passive format or active format, and you record the energy. For the active survey the depth of investigation will be lesser than the passive MASW technique. And then this is the field survey of the MASW. Here you can see there is the source which is being excited, and the hemispherical wavefronts are traveling from here to the distant receivers. So this is the larger wavelength wave, this is smaller, and then even smaller. So larger the wavelength, penetration will be the deeper, smaller the wavelength, penetration will be less. So this is the dispersion, and then this dispersion can be converted into the 2D section of the shear wave velocity. And now this is another field setup, like this is just explaining you can use either the active survey or you can use some kind of passive noises in order to do your MASW surveys. And the active MASW do use some active sources such as the sledgehammer, and you can produce a 2D VS profile, but the maximum of the depth of investigation between in the range of 10 to 30 meters. On the other hand, the passive MASW can give you the deeper estimates of the velocities, and if you do use them in the format of two kind of survey styles, like passive remote MASW, passive roadside MASW. So passive remote takes more space. Here the geometry of the receivers will be symmetric. You cannot have a irregular asymmetric geometry of the receivers, otherwise the noise will be in a particular direction. So passive roadside survey needs a smaller area for the investigation. You can do it in a roll along mode, and then you can in the roll along mode you can produce the 2D shear wave velocity profile along the roadside. Now so the best way is to combine both of them together, active and the passive surveys. Active survey will give you the estimate of the shallower features of the subsurface, while the passive may give you the deeper estimates of the velocities. Now we will go further. Now we will start the class that in which we are going to learn about the refraction and the reflection seismology. Okay, so refraction seismology, we are going to learn about it today. Thereafter, tomorrow we will learn about the reflection seismology. So why refraction seismology is useful? Because it can be used to identify the subsurface layers, bedrock depth. It is safe, cost effective, and also you can detect faults, weak zones, and these faults and the weak zones can increase the risk in the area. If you detect them, then possibly you can design your structures accordingly. And this can also be used to measure the seismic P and S wave velocity for the site response analysis and the microzonation studies. Also, you can assess the soil compaction and rock properties, and then evaluate the liquefaction and site amplification potential. And it also provides the input for the earthquake resistance design and by modeling wave propagation and the ground motion. So what we actually do? So in the fundamental seismological studies, you have some data. So basically you are recording some data using your field setup, maybe some kind of geophones you have a source, you are exciting the source and recording your seismological data onto the receiver. And the data will be recorded in the format of travel times of the various seismic waves, and those seismic waves travel time will be maybe associated with the refraction or maybe associated with the reflection. So for example, let's suppose there is this surface here, and on the surface you have a source and you have receiver. Okay, let's suppose some receivers are there, and from the source you are exciting some energy like this, and this energy will reach to these receivers. Okay, there is some interface underneath. When it will hit the interface, some of the energy will be traveling as a reflection to the receivers like this, and some of the energy may basically refract into the second medium. And if it is critically refracted, then it may also travel along the interface of both of the layers, right? That we call it as a head wave. Okay, so in terms of head wave, we are using the refraction data. In terms of the reflection, we are using the reflection travel time data. Okay, so both the data are useful to give you the information about the source, about the medium, about the depth of the interface, about the velocities of the layer, and that is what we actually would like to do. So how would you do it? For that purpose, you can do the inverse or you can use the forward modeling. Okay, so while doing the inverse, basically you are trying to get from the data, you are trying to get the model. Okay, in the forward modeling, from the model you are getting the data and trying to fit the data. Thereafter you are getting a best model, and that will be your indicator of the shear wave velocity. So what is the fundamental of refraction seismology? So this is the major application in terms of you are trying to find out the earth structure, such as the P and S wave velocity distribution and the density. And in this particular part of the seismology, you are going to use the arrival times of refracted waves or reflected waves, and these arrival times may be used to infer the distribution of the seismic velocities, and that is perhaps the indicator of the elastic properties of the soil. Okay, so using this, we are going further. Then first we will start with the refraction seismology. Okay, so in refraction seismology, you are going to use the travel time of the critically refracted wave. So travel time of the critically refracted wave, that will be traveling along the interface of the two medium. So now look at this geometry. You have the surface here and you have the interface here, right? So there is some source located and there is some receiver over here. And if we consider the source location at the origin and the receiver is located at a distance of around x from the source, then we are exciting the source, and from the source there will be some rays. Maybe the energy will go directly to the receiver in this format, and that is represented by this red color line, and maybe the energy will go down and reflect off from the interface and will reach back to the receiver. Okay, so that will be the two-way travel time because it is a flat interface. So the So the angle of incidence will be equal to the angle of reflection here. Okay. So and also there can be one more possibility that the ray is coming to the interface at the critical angle, then some part of the energy will be traveling at the interface of both of the layers. So this is the interface where this energy is traveling, and this we call it as a head wave. Okay. Thereafter it will go back to the receiver. So this is what it may happen. So you can see the velocity of the first layer is V0, velocity of the second layer is V1, that is we call it as a half space, right. So the governing principles that you see here will be the Snell's law, Huygens principle, Fermat principle. I think Professor Utpal Datta sir has told you about Snell's law, Huygens principle and the Fermat principle, right. What is Snell's law? Snell's law is nothing but R1 sin I1 upon V1 is equal to R2 sin I2 upon V2. Okay. So because we are going to use the flat layer geometry of the earth, so this Snell's law is basically useful in case of spherical earth, where you are dealing with the large distances from the center of the earth.
These things has been taught.
Okay. And then this will be your R1. Okay. Likewise, let's suppose there is some energy that is going from here and then refracting like this, and this here you want to do another investigation, so it will be your R2. Okay. But these distances are basically having some differences between them. Okay. Because you are going to deal with the layers of the earth. Okay. If you are going to use the shallower seismology, then you are going to consider that your layers are going to be flat. Okay, flat layer earth model. So all the models, all the layers will be near to the earth's surface. Okay. So in that case what will happen? This R1 and R2 will become equal and it will be cancelled out, and for the flat earth sin I1 will be equal to, by V1 will be equal to sin I2 by V2. So this is your Snell's law that we are going to use. Okay. So in case of critically reflected ray such as the head wave, the I2 value will become 90 degree. Okay. For example, if you look at this particular point here, and here you will apply the Snell's law, so then it will become sin IC by V0 will be equal to sin 90 degree divided by V1, and this will be equal to 1. Okay. So basically your IC will be nothing but it will be sin inverse V0 upon V1, right. So this is what we are going to use in this. Now you can see the distance between the source and the receiver is also known as offset, that we call it as X, and the direct ray path, if we talk about the direct ray path, what will be the time it will take? If we denote it by TD, T in subscript D, then the time it will take will be X upon V0. Okay. This is the travel time of the direct wave. Okay. So if you want to basically plot it over the travel time curve, here you have the X, here you have the time, then it will be what? It will be a straight line that will pass through origin, right. It will be a straight line that will pass through the origin, and the slope of this travel time curve will give you the velocity of the first layer, right, top layer. Okay. So this will be your tan theta is equal to 1 by V0. Okay. So this is your travel time curve for the direct wave. Likewise, if we talk about the reflected wave, okay, so reflected wave is denoted by this green line here. Okay. And this is going down at the interface, it is reflected off and coming back to the receiver, and the angle of reflection will be equal to the angle of incidence. And if you want to calculate the travel time for the reflected wave, then it will be 2 in bracket x by 2 whole square plus h naught square to the power 1 by 2 by v naught. So this is the total travel time for the ray going down and then coming back up. So if you want to calculate how much distance it is coming from source to this point here, then you can just take the Pythagorean theorem, and then it will be x square by 4 plus h naught square to the power 1 by 2, and because it is a two-way travel time, then it will be twice of that, and divided by the velocity of the first layer. And that if you will rearrange it, it may look something like this, and this particular thing is basically telling us that the travel time curve for the reflected wave will be a hyperbola, because this is a hyperbolic curve here. Okay, so it will look something like this. So if you will plot it onto the travel time curve, here you have the distances, here you have the time, then it will look something like this. This will be your hyperbola, because this is something which is called as the intercept time of the reflected wave. Okay, or you can say the delay time. Okay, so this is the reflected, this is the delay time of the reflected wave of the, or the intercept time. So this is your intercept here that we can talk about. So this is the intercept here. Okay, now if we go further, for the refraction seismology, if we talk about the total travel time of the head wave, then it is the head wave, often referred to as the refracted wave as well, and that is marked as purple color. Okay. In this case, the downgoing wave impinges on the interface at an angle at or beyond the critical angle. Okay, so it is going down, and if it is a critical refraction, then it will go along the interface and then will come back to the receiver, right? So if you want to calculate the travel time for the head wave, then you need to calculate how much time it is taking for going down, thereafter how much time it is taking for traveling along the interface, and then how much time it is taking for coming back up. Okay, so for that purpose you can just make a simple geometry like this and then calculate what is the distance in this one. If we call it, let's suppose this is your A, here it is your B, this is your C, and this is your D. So how much will be the AB? Okay, so that you can calculate by just applying some cosine or tan or sine functions, and then you can readily calculate this AB distance. Okay, likewise you can calculate the BC distance by subtracting from X these distances. Okay, this total distance is how much? This is your X, right? And if you can calculate how much is this one, let's suppose this is E here, this is your F. Okay, X minus AE plus FD. So X, so total distance, so X is X minus AE plus AE plus FD. So AE and FD will be equal, so you can take the difference. So I think it is easy to understand. So total travel time for the head wave will look something like this. Okay, so in this you can use the Snell's law for the critically refracted wave, that is sin IC is equal to V0 by V1, and then you can find out the value of cos IC from this, and then you can also calculate the value of tan IC from the same formula of Snell's law. Okay, after you incorporate all this thing in the form of V0 and V1, then your head wave travel time will look something like this. So THX is equal to X by V1 plus 2H0 in bracket 1 by B0 square minus V1 square to the power 1 by 2. So this is what you are getting. This is the intercept time again you are getting, and this is your what? The slope. Okay, it will give you the slope of the head wave. So if you look at this, so this is the intercept time. Okay, so tau, so this has been represented by tau 1. So this particular thing here has been represented by tau 1, and this tau 1 is what? 2H0 in bracket 1 by V0 square minus 1 by V1 square to the power 1 by 2. Okay, so this tau 1, so travel time curve of the head wave, if you want to look at, it looks something like this. So this is the reflected wave in the form of hyperbola, and this is the direct wave here, this is thing, and you have the head wave. Okay, one thing you may notice that the direct wave is asymptotically touching the reflection hyperbola. Okay, and the head wave is this one. So why the head wave is having the slope lower than the direct wave? Because the direct wave slope is 1 by V0, and for the head wave the slope is 1 by V1. So V1 is greater than V0. As you go deeper, the velocity generally should increase. We are considering that the V1 is greater than V0. So that is why the slope of the head wave is smaller than the direct wave here. So wherever the head wave is crossing the direct wave, so this is the point where they are crossing, and this point is known as the crossover distance onto the x-axis. So if you take it down and measure it from the origin, then it is a crossover distance. So what is crossover distance? So you can see that in this particular thing, let me rub it. Yes. Okay. So you can see that in this, so there is this direct wave. Okay, this is traveling with the velocity of v0, and this head wave that is going down, traveling along the layer's interface and then coming back up. Okay, so initially the direct wave will be the first arrival. Okay, but as you go far in the distances, as the x will keep on increasing, then what will happen? The head wave will be basically start to come earlier. So we want to find out what will be the minimum distance at which the head wave is coming earlier than the direct wave. That will be known as the crossover distance. So why it is happening? Because head wave is traveling in the high velocity layer. Some part of the head wave is traveling in the high velocity layer. That is why it is start to coming earlier than the direct wave after a certain distance. And that minimum distance at which the head wave is coming earlier than the direct wave, that is known as the crossover distance. And there is also a concept of critical distance. So what is critical distance? So critical distance is like let's suppose this is the surface and here you have the interface, right? So there you have a source, there you have a receiver, and then the source is sending some energy and this is being reflected, okay, and it is making some angle I, okay. Likewise, more energy is coming, energy, and it's being reflected, some energy is coming, it is being reflected. So you can see gradually the incident angle is increasing. So the angle at which, the smallest angle at which the head wave start to appear, okay, because in the critical for the critical refraction you need a certain angle after which the energy will start to completely reflect back, okay. So this is the first instance where the head wave start to appear, and this distance onto the surface from the origin will be known as the critical distance. Sorry, not this distance, this distance after the reflection, this distance will be the xc, the critical distance. Are you getting me? Okay, because here it will be received at the receiver, okay. So this is what it is written. At some point for the crossover distance, the travel time curve crosses the direct wave, and beyond this point the head wave is the first arrival even though it traveled a longer path, okay. So they are talking about the crossover distance. This occurs because it travels with greater speed in the underlying layer. Likewise, they have also talked about the critical distance. So if I will ask you what is the value of the critical distance, okay, so this is again the surface, you have the source, you have the receiver, and this is the angle at which the head wave has started to appear, okay, and this angle is how much? This is your IC, okay, and after reflection it is being recorded at the receiver, okay. So what is the distance xc? X is total distance, this one, right? So how much is the value? So here here the thickness is h0 of the first layer. So how much is the value of xc? Xc will be 2h0 tan IC. Do you agree? So
At IC we will get wave.
Not way. At IC, critical distance, we get gate wave. Suddenly, how that reflection comes, but after firing some fight, you got me to your side.
no, this is the first distance where the head wave start to appear. Okay. So at this point, after this, the head wave will start to appear along the interface. and it will travel with the velocity of second layer, that is V1. Okay, so we will consider that it is the reflection, and here along the IC angle this is happening. So when you take 10 IC, how much it will be? XC. So this will be how much? This one. This is XC by 2. So this is XC divided by 2 by V0. H0. Okay, so how much will be the XC? XC will be the 2H0 10 IC, right? So this is what it is written here. Now, so now the question comes, why this basically is known as head wave? Head wave, why head wave is called as head wave? Any idea? Because after the crossover distance, it is started to come earlier.
That is why it is known as head wave. Okay, so see, 5%. Okay, yeah, this is what it is written. So this arrival is called head wave because after the crossover distance, it reaches before the direct wave. Okay, now I think the crossover distance formula. Crossover distance is denoted by x in subscript small d. Okay, how would you find the crossover distance? Just you can equate the direct arrival time with the head wave time, because that is when they have started to appear earlier. So that is the point. Here they will be
equal, time is equal. Okay, then xd is equal to, when you will do that and after you solve the things, so xd will be equal to 2h0 in bracket v1 plus v0 divided by v1 minus v0. So hence the crossover distance depends upon the velocity of the layer and the half space and the thickness of the layer. So yes, from the formula it is being said. So xd is equal to, xd is basically depending upon the h0, it is also dependent upon the v1, v0, all those things. Now what does it tell you? Let's suppose if you are given only this curve. So when you are doing your survey and you have recorded your data, you will see your seismic section. In the seismic section, you can identify your reflected wave that will be coming in the hyperbolic format, and you will be having your head wave also that will be coming in this format, and you will be having your direct wave that is coming like this. Okay, from this seismic section, you can basically find out many things. Okay, if you find out the slope of the head wave that is arriving in the seismic section, then what you will get? You will get the velocity of the half space, right? If you take the slope of the direct wave, then you will get the velocity of the top layer, right? And if you measure this distance onto the seismic section, that is your crossover distance, and then incorporate into this formula here, then what you will get? Because you already know V0 and V1, then you can get the thickness of the top layer. Okay, so and also you can also find out this intercept, right? The intercept formula was given, so this is the intercept formula. If you do not want to use the crossover distance formula, maybe in the seismic section it is not clearly visible, then you can use this one. So tau 1 you can find out from the intercept time, and then you can incorporate everything V0 and V1, and you can find out H0 again. Okay, so this is the utility. Now, so we were talking about the very simple case where you were having only a single layer above the half space. Okay, now if suppose you have n number of layers. Okay, so for n number of layers, let's suppose this is your surface, thereafter you have another layer, thereafter you have another layer. Likewise, there are many layers. Okay, there are many layers. Okay, so let's suppose this is the surface. Surface we are representing n is equal to 0, and there is n is equal to 1, and then n is equal to 2. And thereafter n is equal to n minus 1. So n number of layers are there. Okay, so what will happen? There is a source here, and here you have a receiver, and source energy will go down, then refract, then again refract maybe, and then head wave will appear and then go back and then recorded at the receiver. Okay, head wave will appear at each of the interface. I have just given you the idea that it is like that it is happening. Okay, now if you want to write the formula for the travel time for the head wave that is at the top of the nth layer, then you can extrapolate the previous formula. So previous formula says that it should be equal to x upon v1 plus some amount of intercept time. Okay, so for the nth layer it will be thn plus is equal to x upon vn, that is the last layer velocity, plus tau n, that is the intercept time. Okay, if you want to find out this tau n, then you can use this particular relation. That is the same thing, tau n, where there also we were using the tau. So this was the tau here. Okay, this also can be extrapolated, sorry. So for extrapolation, when you do it, it will look something like this. So you will have to do for each layer, and then sigma j is equal to 0 to n minus 1, and then this should be actually not I, this should be j. So hj in bracket 1 by vj square minus 1 by vn square. Okay. Now if you want to calculate this tau n, you need to have the value of hj, vj and vn. Okay, for this purpose you need to basically use a iterative process. So first you need to solve it for the first interface. From the first interface you will get the h naught, you will also get the v naught, you will also get the v1, and thereafter for the second interface you will have to do it. From there you will have to find the velocity v2, v1 already you have find out, and then h1 you need to find out. Okay, so basically let's suppose if you are dealing with n number of layers, let's suppose this is your travel time curve. Okay, here you have the x, here you have the time, and here you have the there is some direct wave. So direct wave will be same, right? Even in single layer, even in the n number of layers, because that is traveling directly from source to the receiver. So direct wave will be there, and that will be having a slope of 1 by v naught. But that head wave will change for each of the interface. Okay, as you go deeper, the slope of the head wave will keep on reducing because velocities are increasing. Okay, so this is the first interface head wave, let's suppose. This is the second interface head wave, let's suppose. This is the third interface head wave, let's suppose. Okay, that is what you can get from your seismic section. Okay, after you do the observations in the field, you may get something like this. And for each of the head wave, you can calculate your slope, that will give you the velocity, right? And from the intercept of this at the back, if you put that into the intercept formula, then you can possibly get the h naught, h thickness of each of the layer. So recursively you will have to solve it, and recursively when you will solve it, then the formula for the thickness of each layer will come out to be like this. And you can possibly incorporate your n values into this formula, or sorry, j values, this should be j. Okay, so the j values into this formula, and then you can get the values of thickness. Okay, now let's suppose there is this two layer case. Okay, so two layers over a half space. So you have this one layer which is having the velocity v naught, there is another layer which is having the velocity v1, and then there is a half space as having the velocity v2. The top layer's thickness is h naught and h1. Okay, so there is a source, there is a receiver. For the first layer the reflection will happen, and also there will be some energy that will be traveling along the interface as a head wave, and there will be direct wave also. And so that will be happening for the second interface as well, the same thing. So for the second interface, the reflection might be happening like this. Okay, and then you will be having the head wave like this, that is traveling along the interface. Okay, so when you record this section, your seismic section or travel time curve may look something like this. Okay, so in the travel time curve, what you see? You will see a hyperbola. two hyperbolas will be there because two reflections are happening. Okay, so this is the first hyperbola that is represented by R1, and there is another hyperbola that is your high R2. Okay, and you will also see a direct wave, that will be your direct wave that is traveling like this, and it is touching the first hyperbola asymptotically. Likewise, you will be having the head waves. So this is the first head wave that is traveling at the interface of first and the second layer. There will be another head wave that will be traveling at the interface of second and the half space. Okay, and you can take the slope, get the many other things, and also crossover distances and whatever. Now, there are some limitations to this. So refraction seismology has some limitations. So first limitation is the presence of low velocity zone. In case, let's suppose there is a low velocity zone, because at the low velocity zone, what is the low velocity zone? As you are going deeper, there at some point what is happening, the velocity of the deeper point is smaller than the shallower point. That is your low velocity zone. So in this case also it is happening. So there is a source, there is a receiver, and there is this geometry. This is first layer, second layer, third layer, then you have a half space. Okay, so for the first layer velocity V0, then you have V1, and suddenly the velocity had reduced V1 to V2. So V2 is less than V1. It should be less than V1. Okay, V2 is less than V1. Then in that case, what will happen? There will be no head wave. Okay, so if there would be no head wave, then your travel time curve will not be having any appearance of the slope of 1 by V1. Okay, so you can see 1 by V0, 1 by V2 and 1 by V3 is there, but there is no head wave associated with that interface. Likewise, there is another limitation. If suppose there is velocity contrast is there, velocity is still increasing, but it is not increasing that much. There is a very small velocity change, or you can say there is a very thin layer is there of. Okay, so in that case the head wave will appear, but it will be appearing very small that you cannot even identify it. Okay, that will be another limitation to this case. Now since we were talking about the flat layers, now we can also talk about the dipping layers. Okay, so it is not possible that everywhere you will be having the flat layers. Okay, there might be a possibility that you can have the dipping layer. So in that case, you will have to basically perform your survey in a different style. Okay, so you will have to do reverse profiling. That means you will have to basically carry out your survey in down dip direction and also in the up dip direction. So what is the down dip direction? Let's suppose you have your surface and there is some layer that is dipping, maybe like this. Okay, so this is your source here, and here you have a receiver. Okay, if your receiver is in the down dip direction from the source, then it is a down dip direction. Okay, is along the down dip from the source. So this is your down dip from the source, and your receiver is located. So this is your down dip direction. Okay, if it is in this direction, then it is your, if your receiver is here, then what it is? This is your up dip direction. Okay, but in reality what happens? We do not know where the dipping is happening because it is not seen from the surface. Okay, it is buried. So in that case, we don't say it as a up dip or down dip. We just call it as a forward or the reverse profile. Okay, we call it forward and reverse profile. And it is your choice which one you want to call it reverse, which one you want to call it forward. Okay, so now in this particular case where the layers are dipping, so in the flat layer earth, when the layers were flat, you were able to find out the velocities of the layers by taking the slope of the head wave, direct wave. But in this case, the head wave will appear, the direct wave will also appear, but their slope will not be the true velocities of the layer. Okay, they will be the apparent velocities of the layer. Okay, so now when you do your shooting, so that is known as, when you are shooting in the down dip direction, then it is known as that, it is known as shooting down dip. When you are having a receiver along the up dip direction, then it is called as shooting up dip. Okay, so now, so there might be this scenario. So the difference between the up dip and the down dip. So let's suppose this is the source. Here you have a receiver. So this is in down dip direction, because you can say from the source the receiver is in the direction of down dip. Okay, this is in down dip direction, and in this case it is in up dip direction. In both the cases, if you compare with these two, in both the cases the travel time will remain same. Okay, but if you look at this geometry where you are basically keeping the source at one place and then having the receiver in the down dip direction, that means here, and also you are having your receiver in the up dip direction on the other side. Okay, so you can say one is forward modeling, forward profiling, another is the reverse profiling. Okay, so in that case what will happen? In this case the travel times would differ, because obviously the head wave is basically sampling the different part of the dipping layer here, and here also it is sampling the different part of the dipping layer. So that means the travel time will be different. So this is what it is written. So in that case, when the travel times are same and you are just interchanging the position of source and the receiver, that is called as principle of reciprocity. Okay, where the travel time will remain same. So if the source and the receivers are interchanged on a reverse refraction profile, the travel time is unchanged, and this is known as principle of reciprocity. Different up dip and down dip travel times occur because for a given source position, waves going same distance along the surface in opposite direction sample the different dipping interfaces. Okay, that is why their travel time will be different. Now come to little bit of mathematics. So now you see there is this surface here, and there you have the dipping interface. Okay, the dipping is happening at an angle theta. Okay, now you have a source, you have a receiver, and the distance between source and receiver is x, and the perpendicular distance from the source to the dipping interface is HU. Okay, is HD, sorry, this is HD. Okay, and the perpendicular distance from the receiver to the interface is HD plus x sine theta. Okay, you can see it should be like this. Okay, now there is a wave that is traveling down and then traveling as the head wave and then going up and being received at the receiver. Okay, that may be the one scenario. It may be also scenario, so this is a down dip direction. Okay, and it may be possible that your receiver is on this side at the same distance, and then it will be up dip direction. So first you are going to find out the travel time for the down dip head wave. Okay, so that is what we are going to do. So this is the travel time of head wave in down dip direction. Okay, so this is the, and that will be equal to what? That will be the travel time along the interface plus travel time of this particular part and this particular part. Okay, that will be summed up together and that will give you the total travel time. So this is what it is happening here. So they have calculated and it came out to be this particular thing is travel time along the interface, and this is the travel time of the upgoing and the downgoing wave. So this is the downgoing wave here, this part, and this part here is the upgoing wave, isn't it? So when you sum them together and just readjust them, and then finally you will get this particular thing. This is the total travel time of head wave in down dip direction. Okay, and if you will just rearrange it, then it will be similar to what? X upon Vd. So what you see? There is X also, and this particular term is there. If we somehow call it as 1 by Vd, then it will go like this here, and there will be this intercept time tau d for the down dip head wave. Okay, so which is the equation of the straight line? So this is the equation of straight line. This is again the straight, head wave is straight line in the previous case also, but here the velocity or the slope will be different. Okay, so slope of this particular line will not be the true velocity of the half space. Okay, it will be the apparent velocity, because you can see what is the Vd value. Vd is how much? Vd is V naught divided by sine Ic plus theta, right? This is the Vd. Likewise, if you change the position of the receiver in the up dip direction, what should be the travel time of the head wave? That will be something like this. That will be the up dip direction. Okay, and here if you will see, the term Vu has appeared because we are doing up dip. So Vu. So Vu will be equal to V naught divided by sine Ic minus theta. That is the apparent velocity. Okay. So now,
So this PD, so PD into sine I suggest that was empty on the moment. We are interested in quite different being on two sides to plus theta, and then if you did the property sign there as to a transferring of one. So if you get the number when it goes for each other, we not an ED is this code. Just such get yeah, there will be change, right? Do you accept that there will be change? It is not representative of the true velocity. So that is the apparent velocity. Okay, we will see how to calculate Ic theta
and other things. So, one you have the travel time for the upgoing wave in the up dip direction and in the down dip direction both, right? So now if you will plot it on a travel time curve, let's suppose on the x-axis you have the distance, okay, on the y-axis you have the time for the forward profiling and for the reverse profiling, okay. So maybe one of them you can, so there is also is the travel time, okay. So actually we are merging two travel time curves together now, okay. So what you are doing here, so direct wave in both the cases will be having the same time, right? So this is the direct wave up to here, and for the reverse profiling this is the direct wave, okay, and both of them are having the same slope 1 by V naught, okay. Thereafter the head wave comes. So this is the head wave for reverse profile, and this is the head wave for the forward profile or up dip or down dip, whatever you want to call, okay. So what is the slope of this? 1 by Vd, right? And what is the slope for this? 1 by Vu, okay. When you extend the head wave of the down dip, then it will intercept somewhere here, and that will be the intercept time tau d, okay. So tau d we saw that, right? This is the tau d, and this value is there, tau d, right? Likewise you have tau u also, and its value is here. So for tau u you need to extend this head wave, and this will be the tau u. So tau u and tau d, do you think both are same or different?
Okay, first of all, tell me which one is more, Vu or Vd? 18. Vu will be more. Okay, because it is V naught by Ic minus theta, sine Ic minus, that is V naught by sine Ic plus theta. So in the up dip direction, the apparent velocity will be greater than the down dip direction, right? And if you look at these values of tau u and tau d,
then can you make out anything?
Yes. Like which one will be greater, which one will be smaller. Counting. Why? Because the perpendicular should be the XU or the STP is being actually rational test. And HU is under the text. Yeah. So tie will
So it is natural, you can easily see it, right? Which both of them are not equal. Okay, so so from this curve, you can find out the apparent velocities. Okay, Vu and Vd, and when you incorporate them into these formulas, and V naught you can find out by the slope of the direct wave, right? You have the direct wave velocity. You also can find out the Vu and Vd. So you have two equation, two unknown. Ic and theta are unknown now. All other things have been found out, right? So you can easily find out Ic also. You can easily find out the dip of the layer also, interface, right? Now, so these are the formulas. So these are the formulas which were derived from these two formulas. So you have Vu. So Vu is equal to V naught upon sine Ic minus theta, and Vd is equal to V naught upon sine Ic plus theta. And when you will rearrange them, sine inverse something, then you will get these two formulas, theta and Ic. Okay. So these are the formulas that you can use it for finding out the dip angle of the interface and also the critical angle of the interface. So in case of the dipping geometry, so most important things are these curves, travel time curves. Okay, once you get it, you can basically find out many things like what is the crossover distance, what is the velocity, apparent velocity of the head wave. Okay, you can also find out the direct wave velocity. Okay, and thereafter you can incorporate these formulas into the equations to find out HU. Also you can find out what is the perpendicular distance from source to the interface, what is the perpendicular distance from receiver to the interface. So that will be represented by HD. Okay, so all these things you can easily find out. So if you compare with the flat earth geometry, so just see that again. So in the flat layer geometry, you were basically having a head wave that was giving you the true velocity of the layer. Okay, but in case of dipping interface, you were getting the apparent velocity of the layer. Okay, and in both the cases, you were able to find out the velocity of the top layer from the slope of the direct wave. Okay, and there were two limitations to the flat layer case. Like first limitation was, if there is a low velocity zone, there will be no appearance of the head wave, and if there is a very thin impedance contrast, then the head wave will appear, but it will not be clearly visible. Okay.
this X because it happens below some framework rules that doesn't miss it. Is there some conditions that would take on that solutions? And this is we can so say that simple. Actually, this is actually we do not okay. When we do our survey, we have a channel number of
geophones placed along the line. Okay, so on all the geophones we are recording our energy. Okay, so X is basically varying. Okay, when you want to cover a larger line, then you can move along the roll along mode and then keep on doing your survey, keep on shooting, and thereafter you then you collect the data. Okay, any other question? Okay. So what is the use? So this refraction seismology has been used. I am taking you a little bit farther away from the engineering seismology. So the refraction seismology has been used to find out the crustal structure also. So there was a scientist. So you know what is the name of the discontinuity in between crust and the mantle? Okay, Moho discontinuity. Okay, that is the abbreviated form of Mohorovičić. Okay, that is the name of a scientist. Okay, so Mohorovičić discontinuity was basically discovered by this scientist in 1909, and he observed by taking the refraction profile that there are the two arrivals associated with the P waves and two arrivals associated with the S waves are coming in the travel time curve. Okay, so he plotted something this kind of travel time curve. Okay, so what he observed, there are the P wave velocities which are coming at a higher velocities like 7.7 kilometer per second. That means they were having larger slope or smaller slope of the head wave. If they are having higher velocity, so 1 by V naught will be small. Okay, so they were having the smaller slope. Okay, so he observed that there are the two waves
in which one wave is traveling with a higher velocity. That means it is coming from a deeper structure. Okay, and there is a direct wave which is slower and coming from a shallower wave, right? So you can see like there are these two waves. They are the two waves. These are coming, and he called them as PN and PT.
So Pg being coming from the crystal part, Pn being coming from the mantle part of the earth. Okay, G means granitic. Okay, and so he calculated their slope and then found out the velocity, and which came out to be 7.7 kilometer per second and 5.6 kilometer per second. So he observed this significant contrast between the velocities between these two layers, and he called this discontinuity or boundary between these two layers as a Mohorovičić discontinuity, and same feature he has observed for the shear wave as well. So that is how he was able to find out what is the depth of the Mohorovičić discontinuity at the location of the survey, and also what is the average velocity of the crust and what is the average velocity of the upper mantle. Okay, so that is all for today. Thank you.